So you can basically predict anything because of how many different ways there are of assembling the universe. Is it Googleplex literal or just like a figure of speech?
It's quite literal in the sense that the 10 to the however many powers Googleplex is pretty much matches the amount of vacua that you can get from string theory.
It is, I believe, 10 to the 10 to the 100, which is unfathomably big. I mean, even 10 to the 100 is pretty big.
Mm-hmm. Yeah, and this is where the string theorist version of the multiverse comes from.
Hi everyone, I'm here at City Tech with the Dean of the School of Arts and Sciences, Professor Justin Vazquez-Poritz, and I'm also here with a professor of physics at City Tech, Professor Andrea Ferroglia. So I'm very excited to be with them here today. I took courses here at City Tech, actually one specific course, Physics 2, along with its lab component here at City Tech in summer of 2024. And during that time, Professor Vazquez-Poritz really helped me. And lately, I've also been communicating with Professor Ferroglia about a specific project and also generally about physics. I think only 60 years or so, right?
Yeah, I think it was 1946 when it was established, after World War II.
So about 70 years, actually. Mm-hmm. So yeah, I think it's been doing very well with the resources it's been given. Mm-hmm. Well, actually, 1947. That 80th year anniversary is approaching.
It is.
So you're going to have to plan for that.
Mm-hmm.
Also, I believe you became dean in 2015. So I think your 10th year anniversary is approaching as well.
It is. Time travels quickly.
In 2017, something like this.
Am I wearing the same tie?
Looks like it.
It looks like it, right?
Has been focused on diversity and especially admitting students from all 5 boroughs of New York City. So how especially have you made new ground in that field?
So you reminded me of my 10-year anniversary coming up. During this time, I would say my colleagues, not just myself, but it's really my faculty that have done the hard work of developing new academic programs, including our applied computational physics program. We've developed about 4 or 5 new programs in the last 10 years, all within the STEM-related areas, and we've consistently been honored as being a top engine of economic mobility for our students. It means that they come in, they leave City Tech with a degree, and their earning power has increased substantially because of it.
So it sounds like you really help students that are struggling actually make their way in the world. So I think that's a very big role for something that seems like a small college on the outside.
Might seem like a small college, but at one point we had almost 18,000 students. Since the pandemic, our enrollment went down quite a bit, but it's increasing again. Now we're at about 13,000 students.
Well, I mean, you say that like it's not a normal thing. I don't think you can find a single university on the planet whose enrollment went up during 2020.
Right.
So I suppose my second question would be, what about the things that you've done for physics in specific? I know that you work in, I believe, high energy physics specifically. So what is your research area in specifically, and what do you enjoy about that field?
Yeah, so there are different types of string theorists, and I'm of the type that focuses on the gravitational aspect of things. Really, it's general relativity, adding more dimensions, adding things like supersymmetry. And one of my focuses is on trying to find new black hole solutions. And the interesting thing about something like string theory that lives in more than 4 dimensions of space-time is that you could have black holes that have different shapes. In 4-dimensional space-time, it's not possible. A black hole is always the same shape. It's always described by very few qualities. Its charge, its mass, its angular momentum, that's about it. In something like 5 dimensions, you can have, I actually have a prop with me. It was a bagel that I was intending to eat, but I didn't get around to it. So in 5 dimensions, you could actually have a black ring. And you could ask
It doesn't look very black to me, I'm not going to lie.
That's okay. I think it serves its purpose. And you could ask, why doesn't this ring collapse on itself so that it really becomes a black hole? And the reason is because it has a certain amount of angular momentum, and that keeps its stability. And something like that can only happen in higher dimensions.
Oh, so it's like the rings of Saturn or something.
It is, and in fact, I wasn't the one that came up with the solution, but those that did even came up with the black Saturn solution, where you have a black hole at the center and a black ring rotating around it. What I did was I was able to generalize it in certain ways.
So are you going to eat this 5-dimensional black hole, or?
As soon as this demonstration is done, yes.
Is there actually anything inside it, or is it just a plain bagel?
Or he can turn it to a coffee mug.
Yeah, I believe there's just food coloring on the outside. Hopefully it comes with some nice tastes.
I mean, me personally, I wouldn't want like a fruit-flavored bagel or anything.
Uh-huh.
But,
Well, we're in Brooklyn, where we can get practically any bagel that you want, from a French toast bagel to an everything bagel.
I think everything bagels are the pinnacle of bagels, personally. I mean, they're really good. That's all I can say about them. I don't really like those complicated bagels where they basically put an entire burger between the two patties. I mean, if you want a burger, just make a burger. Don't make a burger with a hole in it. That loses a bunch of the structural integrity.
Yeah, we're in a country that puts fried chicken in waffles, so anything goes, right?
I mean, yeah, but personally, I don't want, like, my sandwich or whatever I'm eating to fall apart. And burgers are already, like, really prone to falling apart because of how smooth their inner surface is. So, like, then when you make them with a giant hole in the center, it just gets messy. And, okay. I don't know how I went on that tangent. Do you, as Dad said, do you have any plans on turning this into a coffee mug of any sorts?
Of turning this into a coffee mug? So, topologically it would be the same, right? Mathematically you could argue it already is a coffee mug, but if you try to actually use it as a coffee mug, as you can see, the coffee would just go through the hole, so that wouldn't be very successful.
You can always improvise, like cut a small hole directly into the bagel and pour the coffee in there. But then again, the bagel might just soak it up, become a coffee-flavored bagel. Okay. The third question is about string theory, actually. So what I would like to ask is, it's been known, or at least hypothesized for years, that quarks are the smallest division of matter. The 3 little subdivisions that make up every subatomic particle. So, do you think there's anything smaller than quarks? And also, why have we never been able to separate a single quark from its group of 3? Why are quarks so clingy to one another?
So I'm going to let Professor Ferroglia answer the second question while I answer the first one, because my answer to the first one is very easy. I don't know. And the reason no one knows the answer to that, right? We can only know the answers to questions that we have enough energy in our particle accelerators to probe. And it might be that we've reached the most fundamental particles there are, and there's nothing beyond quarks. Or it might be that, a million years from now, when we can probe, much higher energy, we'll find that there's something even more fundamental. I will say that the aspects of space and time change as you go to scales so far down as a quark, where quantum physics comes into play, and that brings about this notion of minimum distance in space and time. That makes sense. And so in that sense, once you hit the Planck length, it might no longer make any sense to say, is there something smaller than that? That might be the smallest length scale it is, or it might be that at that point, the very notion of space and time breaks down. Reality is described by something that no longer involves space and time. In order to know the answers, we would need to have some quantum theory of gravity, which we don't yet have.
Yeah.
So why are quarks so clingy, Professor Ferroglia?
So they are so clingy because they interact through the strong force that, as we saw before, is mediated by gluons. And the strong force has a very strange property. So first of all, the gluons are also self-interacting, and the force grows in strength with the separation between the quarks. So it's like a rubber band. So when the rubber band is not stretched, the two ends of the rubber band that represent, for example, a quark and an anti-quark in a meson, don't attract each other very strongly because the rubber band is slack. But when you try to separate them, the rubber band starts exerting a force which is stronger and stronger.
So we have the inverse square law.
Yeah, but the analogy goes a little bit further. At a certain point, you can break the rubber band, okay? But when you break the rubber band, you don't get just one end and then the other end. You get two new ends that are formed at the point in which the rubber band is broken, okay? So you still have a pair of quark and anti-quark in the piece of the rubber band that goes to the left, and a pair of quark and anti-quark in the piece of the rubber band that goes to the right.
Oh, so if you apply enough energy, it just makes quarks of its own.
Exactly right. You remember we saw before how a photon, a virtual photon, can split in an electron and a positron. So a gluon can do the same thing, can split in a quark and an anti-quark.
I think the universe just doesn't want us to see a quark by itself.
Yeah.
Maybe it hides the meaning to life or something else that we can't know.
Especially with names like truth and beauty, there has to be some hidden meaning, right?
Well, these days we prefer to refer to them as top and bottom as well. Less philosophical and more practical.
I mean,
or strange and
do you imagine that each quark by itself? What is the need for naming some of them up and down, top and bottom, strange and charming? Like, what's the difference between each type of quark at its core? I know it's the electrical charge, but anything else?
No, there are two types of quarks, the up-type quark and the down-type quark. And the up-type quark are the up, the charm, and the top. And the down-type quark are the down, the strange, and the bottom. And those, up and down, charm and strange, top and bottom, differ because of the charge, okay? Plus 2/3 of the charge of the proton for the top type quark, and minus 1/3 of the charge of the proton for the down type quark. And then each quark differs because from the other ones because of the mass, okay? And typically, especially for the heavy quarks, it is the up type quark that is heavier than the down type quark, okay? So all particles, also the leptons, are organized in families, and then there are 3 of these families. So for each particle in the first family, there are heavier brothers in the second family, and then even heavier brothers in the third family. For example, for what concerns the charged leptons, we have the electron, then we have the muon, that is the same as the electron but with a higher mass, and lives in the second family, is part of the second family, or generation, depends on how you want to call them. And then there is the tau lepton, that is again the same as the electron, but even heavier than the muon. Okay, and that's part of the third family. So similarly, for what concerns the quarks, in the first family you have up and down, and essentially all the matter that we see in this room is made of up and down quarks that are bound into protons and neutrons through the strong interaction. Then in the second family you have charm and strange, and in the third family you have the heaviest elementary particle that we know of so far, which is the top quark, and then the bottom quark. The top is up type, bottom is down type, charm is up type, strange is down type.
Yeah, I think that makes sense. But one more thing I'd like to ask is, what's so strange about strange quarks? Are there like shady business deals that it's hiding from scientists?
I mean, they were strange because at the energies that people were able to probe until the late 60s, early 70s, it was possible only to create up-down quarks, and then particles that had some strange quark, and since it was the new quark, the new kid on the block, that was the strange guy.
Oh.
Okay. Then in 1974, people realized that there is also a fourth quark, which is the charm. That was, or I mean, people already guessed that it had to be there, but so then the second family became complete, and then toward the end of the 70s, the bottom quark was discovered. So it was clear that there was a third family, and then finally in the 1996, I think, at Fermilab in Chicago, people discovered the top quark that was sort of a surprise because it's very much heavier than the bottom quark. So people had to build colliders that were able to probe a much higher energy than the one that was necessary to produce bottom quarks.
Wow, I can't believe that they called it names for just for being different than everyone else. These scientists are real bullies, not going to lie. Are quantum field theory and string theory naturally opposed to one another, or do you think they can exist in a unified framework?
So if one believes in string theory, then your answer would actually be that quantum field theory comes from string theory. Because you can take a string, you vibrate it, and what its modes produce are the quantum fields of quarks, electrons, even gravitons. So not only is it quantum field theory, quantum electrodynamics, quantum chromodynamics, but quantum gravity as well. That's all the good news. Now, of course, the bad news is that this happens in an idealized 10-dimensional space-time. How do you connect that to the real world that we see around us? And it turns out there's a Googleplex number of ways of making that connection based on how you compactify those extra 6 dimensions of space-time. And so not only can you predict that you get the standard model plus gravity, you can also predict any number of other universes that don't match with what we observe around us. And that's the trouble with string theory.
So you can basically predict anything because of how many different ways there are of assembling the universe. Is it Googleplex literal or just like a figure of speech?
It's quite literal in the sense that the 10 to the however many powers Googleplex is pretty much matches the amount of vacua that you can get from string theory.
It is, I believe, 10 to the 10 to the 100, which is unfathomably big. I mean, even 10 to the 100 is pretty big.
Mm-hmm. Yeah, and this is where the string theorist version of the multiverse comes from, because in some sense it's predicting all these bubble universes.
I'm taking differential geometry this semester in preparation for taking general relativity formally next semester. So how did Einstein actually use the tools of differential geometry that were invented by Riemann and the like to formulate general relativity?
Yeah, so in some sense you're going about it in a more logical order than Einstein did, in the sense that you're learning the mathematics that's needed to understand the physics. Now in his day, of course, people didn't understand that connection as it pertains to relativity. And so he was basically doing quite a bit of detective work, where he was looking at things like the gravitational redshift, how does he explain that, and coming up with these kind of partial theories that were able to explain some aspects of relativity, but not others. And one of the things that was missing was this geometrical appreciation of space-time as a single manifold. And so then he went back to Switzerland and he spoke to his old college friend, Marcel Grossmann, who told him about differential geometry. And then it was like a light bulb turned on, and he realized that this basically embodied everything he was trying to do. And very simply, actually, he could come up with these geometric invariants and write actions out of them and vary the action, and then the equations of general relativity appeared. And modern day physicists are able to readily extend general relativity to even more complicated theories of gravity by using differential geometry. So this is going to give you an extremely powerful toolbox.
A loop Like, you remember the loop that we had before with the box?
Like in like knot theory, right?
Yeah, I mean, these are graphs, so graph theory applies, right? So, and then we can build another one loop diagram like this.
Why are I would like to ask, why are some of these shorter than others?
Just for graphical purposes, because you don't want to have lines which are too long, right? So they don't have any physical meaning. The length doesn't have any physical meaning. So on top of the box diagram that you saw before, this is another one loop diagram correction to the Baba scattering. You see that you have again 4 vertices, so it's not so likely as the one with only 2 vertices, but is as likely as the one with 4 vertices that we saw before. But now the loop is a different kind of loop. You have a pair of electron and positron that live for a short amount of time. They are created here and they annihilate here. Okay. So,
These really remind me of those toy like molecule models where you take each of the atoms with
Exactly.
the holes in them representing how many electrons they have, and then like connect them together.
exactly right. So that's precisely the idea. So the idea was that since Feynman diagrams are made of building blocks, one can really make building blocks to play with Feynman diagrams.
It seems like you're having lots of fun playing with them.
Exactly.
So now we can indoctrinate people while they're young.
Exactly. Yep.
I mean, first you'd have to add some color to these.
Sure.
That's a good idea.
Yeah. I mean, I didn't do it because I couldn't ask my poor cousin to build, But the idea would be to have different colors for different quarks or different leptons and so on and so forth.
They're not marketable enough if they're all just light brown. How would we know, hypothetically, that an antimatter bubble would start coming for us?
I think by the time we know it, it would already be
Too late.
And that's the only consolation, is that you won't know it.
I don't think, even if it wasn't too late, how hypothetically will we do anything to stop it?